In this example, we are tasked with dynamically balancing a shaft that carries four rotating masses labeled A, B, C, and D. The masses are arranged along the shaft's axis, each at different radii and angular positions. Our goal is to ensure complete dynamic balance by determining the unknown mass and angular position of mass A, as well as the positions of planes A and D. Here's what we know. Masses B, C, and D have known weights 30 kilograms, 50 kilograms, and 40 kilograms respectively. Their radial distances from the shaft axis are 24 centimeters for B, 12 centimeters for C, and 15 centimeters for D. The planes containing masses B and C are 30 centimeters apart. The angular positions of masses C and D relative to B are given as 90 degrees and 210 degrees respectively. Mass A is at an unknown radius of 18 centimeters, and we need to find its mass, angular position, and the location of its plane and the plane of mass D. So objective is to solve this problem, and we will use the principles of static and dynamic balancing for rotating systems, apply vector analysis to account for both magnitudes and angular positions of the masses, determine the unknown mass and angular positions of A, as well as the positions of planes A and D to achieve complete dynamic balancing. By carefully analyzing the given data and applying balancing equations, we can ensure the shaft rotates smoothly without vibration. So let's proceed step by step to find the solutions to parts 1 and 2. Now here, this slide shows the outline of the key steps and parameters involved to solve the dynamic balancing problem for the rotating masses on the shaft. So let's break down the components systematically to understand the solution approach. First, the reference plane. We need to define the reference plane to analyze the forces and moments. The masses A, B, C, and D are considered relative to this plane, which simplifies calculations. Now, mass C has a weight of 50 and operates at a radius of 12 centimeters. Mass B is 30 kilograms at 24 centimeters, and mass D is 40 kilograms at 15 centimeters. The angular positions of C and D relative to B are given as 90 and 210 respectively. These angles are critical for solving the force components. Now, the distance between planes B and C is 30. This spacing affects the moment calculations for dynamic balancing. So first we'll need to determine the positions of planes A and D to ensure all moments are balanced. We also have to look at calculate the angular position of mass A to counteract and balance forces. Now we are saying that we can let the distance between plane A and B to be equal to x, and the distance of plane D from plane B to be equal to y. This table presents a structured approach to solving the dynamic balancing problem by breaking down the contributions of each rotating mass. Let's analyze each column to understand how we achieve balance. So column 1 has the planes, column 2 has the masses. So the shaft has 4 planes, A, B, which is our reference plane, C and D, and each carries a mass with specific value. So A is unknown, B is 30 at 24 centimeters from the reference plane. C is 50 kilograms at 12 centimeters, and D is 40 kilograms at 15 centimeters. Now, column 4, we calculate the forces. So the force term is critical for static balance. So for example, mass B contributes 720 kilogram centimeters, and mass C contributes 600 kilogram centimeter. Mass D also contributes 600 kilogram centimeters, matching mass C's magnitude. but differing in angular position. In column 5, we have the distance from the reference plane. So dynamic balance requires moment calculations. Distances are measured from plane B, which is our reference plane. So plane A is at minus x left of B. Plane C is 30 centimeters to the left, I beg your pardon, to the right of B. Plane D is plus y unknown right of B. Finally, column 6 is a couple term. So the couple term ensures moment equilibrium. For instance, mass C couple is 18,000 kilogram centimeter squared, and mass A's couple is minus 18x ma. The negative is due to its position. Mass D's couple is 600 y. So we'll use a table to solve for ma by ensuring the sum of the forces cancels out. Also, we'll determine x and y by balancing the couple terms to 0 for dynamic equilibrium. Now we are going to use the graphical method to solve the value of the unknown mass A. And we will have to sketch the first polygon, and I'll explain how we do that. We pick a point O, and using a suitable scale from column 4, where we have the first terms, we sketch 720, which is the contribution of mass B, which is in the horizontal position in the manner that is shown. Then from point B, we measure 90 degrees, which is the relationship between mass B and mass C, and the contribution is 600 kilogram centimeters by mass C. That gives us the position of point C. And from C, we measure 210 degrees, and with the magnitude of 600 kilogram centimeter, we then get the point D. So the gap is equivalent to the unknown mass A, and from there we can then be able to get that distance using the suitable scale. And we now know the position of the mass is placed at 236 degrees, and this ensures both static and dynamic balance. So by measurement, we should be able to get mass MA to be equal to 20 kilograms, and the angle is 236 degrees. Now from column 6, which has a couple terms, we're going then to sketch the couple polygon, and this couple polygon has 3 terms. So the first term is we're going to sketch vector O prime C prime, which has a value of 18,000 kilogram centimeter squared, and its orientation is in the vertical direction. Then the next thing we do is we're going to sketch in the direction that I've shown. The next thing we do is we're going to sketch vector C prime D prime, and this vector has a magnitude of 600 y, and its orientation is the position of parallel to the position of mass D, and finally in that direction. And finally we're going to sketch vector O prime D prime, and this is going to be parallel to mass A, whose value we just got in the previous slide. And the orientation is as shown at an angle of 236 degrees, so that the couple polygon closes. Once the couple polygon closes, then we can now be able to determine by measuring vector CD and OD, we get a value of 22,700 kilogram centimeters squared for vector CD, and vector D prime O prime, we get 35,300 kilogram centimeters squared. Now from table 6, the couple uh, due to mass D, who's given as 600y, and the couple due to mass A, that is vector D prime or O prime is equal to minus 18x MA. So vector C prime D prime is equals to minus 22,700, and it is equal to 600y. So from there we can be able to get the value of y, which is minus 37.8 centimeters. Also, vector D prime O prime is equals to 35,300 kilogram centimeter squared, and it is equals to minus 18x MA. From there, we can be able to get the value of x, as this is the only known. Now, the distances of planes A and D from plane B are LA, which is minus x, and we can now get that that value is 98 centimeters. Similarly, LD, which is equals to y, is actually minus 37.8 centimeters. The distance of plane A, that is LA, is positive, hence plane A lies towards the right of plane B at a distance of 98 centimeters. The distance of plane D, LD, is minus 37.8 negative, hence plane D lies towards the left of plane B at a distance of 37.8 centimeters from plane B. Now we'll use the analytical method also to solve the same problem. So figures A show the position of the masses, which we saw earlier, and figure B shows the angular positions of the masses, MA, MB, MC, and MD, in which mass B is assumed to be along the x-axis. Now let MA to be the mass of A and theta A to be the angular position of mass A with respect to the angular position of mass B. Now, for complete balance, the resultant force must be zero, or the sum of horizontal force components must equal to zero. That is the summation of mr cos theta, and the sum of the vertical components of the force must also be equal to zero. That is summation mr sine theta. So for the cosine times the horizontal components, we can now substitute the values that we have, and when we do that, we end up having it equal to minus 200.4, which is our equation 1. We do the same for the vertical components, that is the sine terms, and when we input the values, we end up having equation 2, which gives us the value of minus 300 to be the sum of the vertical components. So squaring and adding equation 1 and 2, we can now be able to get the value of MA, which is equals to 20.04 kilograms. Also, we can, by dividing equation 2 by 1, we can get the value of the angle theta A, which is equivalent to 236.25 degrees. Now for complete balance, the resultant couple should be zero, and we know that when we resolve the vertical and horizontal terms, they should all be equal to zero. So if we take P as a reference, we know that LA is equals to minus X, LB is equals to 0, LC is 30, and LD is Y. So all the terms which are the cosine times, if we input the values, then we get equal to this equation 3 gives us a value, so that X is equals to 2.539y. That is our third equation. If we look at the sign components of the coupled balance equation and we input the values, we end up having this equation where we can plug in the value of x from equation 3 equals to 2.539y, and now we can be able to get y when y is equals to 37.8 centimeters. And those are the same results that we're getting from our graphical method.